Okay, so last time we discussed the formal way of dealing with probability, which is why designing these axioms, or you define a probability measure as something that satisfies these three axioms, and it's a set function assigns probability. Like probability basically is a set function on events. So A is a subset of all possible events. So we had a sample space, a set of all events, which could be potentially 2 to the omega, which is the power set, all the subsets, if in the case of finite or countably infinite omega, this is doable. Otherwise, there are some issues. We're not going to worry about that. So this P then is defined on A. So it's basically a function that maps elements here to basically real numbers, or um, actually positive reals. The thing is, so we have non-negativity, and then we have a normalization. So the probability of the whole sample space is 1, and then we have the additivity. Okay, so pairwise disjoint events, um, the probability adds up. The probability of the union of them and is the sum of the probabilities. Okay, and then from this we get a lot of interesting properties. Everything else basically follows along with like maybe 2, 3 more definitions, the definition of conditional probability and the idea of independence. Um, Basically, they're like these chief, like maybe ideas in general. Uh, you can build everything out of them. So these properties we went over, some of them proved, some of them you can prove yourself. Just you have to reduce to one of these axioms. I'm not going to repeat that. And then any questions about the setup? So this is perhaps the first most important thing to understand about probabilities. And I'm going to say that something that satisfies, so if a set function satisfies A1 and A3, it's called a measure. Uh, called a measure. Um, and this is where measure theory starts. So um, things 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 that satisfy A1 and A3 but don't satisfy necessarily this condition. So they're not normalized, they're called measures. For example, let's say length on the real line is a measure. So it assigns the typical length to intervals and basically unions of intervals and stuff that has these properties. So it's non-negative and also is additive. But for example, the whole real line, you can't assign uh, like a length of 1 because the length is like the natural thing is like infinite. Um, the like volume is like basically the area in R2, volume in R3. And then the thing is that if the measure is finite in the sense that the assigns um, a finite value, so sometimes these are written like mu. Okay, so you have like mu of like a measure of a set. So if the mu of omega is finite, then you can always divide by that. So you can define a probability measure uh, by looking at this and then dividing it by mu of omega. Then you can easily see that the P of omega would be 1. Okay, because you just apply with A equal omega. Uh, and so turning the probability, like a measure, general measure to a probability measure is just a matter of normalization. You normalize by the measure of the full set. Okay, that's just this aside. Does that make sense to people? So like an example, I mean, I can give you an example. The first thing, so we introduced these measures, but like concretely, how do they look like if you want to write them down? Suppose omega is finite. the simplest measure on it is basically I pick a subset of omega. Um, a natural measure is like the just the cardinality of the set. So let's say that mu of A could be cardinality of set A. Okay, it counts how many elements are in the set, and you can easily see that if A is disjoint uh, um, from B, um, then the cardinality would be basically cardinality of A union B would be the sum, right? So the number of elements uh, in the union of A and B would be the number of elements in A plus the number of elements in B because they're disjoint. So this measure has this additivity property, right? In other words, like we have this property if we define it to be cardinality. Okay, cardinality. And so we can do this procedure. So if the set is finite, then uh, the cardinality of the full set is finite. So I can divide by omega. So this is like the construction that I mentioned. So cardinality of A divided by the cardinality of omega, this is like that mu A divided by mu omega business. If you think of the cardinality as a measure, so this is how we normalize it. So this gives me a probability measure. Okay, give me a probability measure on this finite set, right? Um, does that make sense to people? So you can easily verify that this measure, which counts how many elements are in an event divided by the total number. Another way of seeing it is that the number of favorable cases, so the cases that are in A are favorable, then divided by the total possible cases. Okay, that would give me a probability measure. So this probability measure is um, assigns like equal probability to every element of so omega. So let's say if omega is omega 1, omega 2, omega 3, say up to omega k, it's finite, then you can see that the probability of, let's say, a general singleton, so this is an event. So this event um, is the event that just omega I occurs. Um, and so what is the probability of this event under this model? Oh, there a question. Can you please explain why you're using mu again or what it stands for in this case? Yeah, so I just wanted to give it a name. We use the mu as a generic measure. Here it was a little bit abstract, so it's just it's not a particular thing. So what I'm saying is that people usually denote measures with mu or nu or Greek symbols. And like a probability measure usually with P, or for example, you write it Q and these things. And so what I was saying is uh, if you have a general measure, and if the measure of the entire uh, set, in our case, sample space, is finite, then you can turn it into a probability measure by dividing the measure of this any set by the measure of the total, like the whole set. And an example here would be if you have a finite set, we can define a natural measure uh, like this. Okay, so this is an instance. I'm writing it because I just wanted to connect with the previous slide. Okay, so this is an example of a measure. So we can define mu A to be cardinal. There are other ways of defining a measure, but one way is like for a finite set, you can define mu A to be the cardinality of A. Okay, and it's not negative and it's additive. But the fact is that the mu of the entire set, so mu of omega need not be equal to 1 because only it will be equal to 1 only when omega has a single element, right? So in general, this is not going to be 1. So this mu, this cardinality is not a probability measure, okay? However, if I'm on a finite set, um, uh, the mu of omega, which would be like cardinality of omega would be finite. I mean, th this is how we define omega here. So it's going to be finite, then I can divide by this. So um, if you don't like mu, just use the cardinality, right? It's just a renaming of it. Does that make sense? Did I answer the question? Yes, okay. Yeah, it's just a mnemonic for general measure. In this case, we define it to be like this. So it's like, I want to say it's the same construction as I mentioned here. Okay, it's like a special case of that. So here, mu of A would be like cardinality of A, and then mu of omega would be the cardinality of omega. So in general, this is how you can normalize any um, measure that has a finite total measure. In this case, would be like rather simple. So my question was that if we have a set, finite set, if I look at a singleton event under this model, this defines like a full probability model because we specified the set of all events is all the possible subsets, let's say, and then we have specified P as well. So we have the sample space, we have the set of events, and we have P. So we have a full specification of probability model. Now the question is that once I have this, I can assign, I can tell you what the probability of all possible events are. So this is a possible event. What is the probability? That's the question. Anyone? Any? No one? So it's just what is the size of this? Like what is the cardinality of the set? One. Yeah, so it's going to be 1 divided by the cardinality of full set. In this case, I wrote k, so it's going to be 1 over k. Um, in general, it would be just you can write it as 1 over like cardinality of omega, like this. And so the fact is, this number doesn't depend on which singleton set you pick. So all of them, so you can see I is like anything, like I is 1 through k. For all of them, the probability is the same. So all the outcomes are equi-probable, okay, or equally likely. So this model is a model that uh, assigns equal probability to all the outcomes, okay. So for this reason, we call this the uniform model. So it assigns probability uniformly over the entire sample space. Okay, it doesn't favor any one particular outcome over the other. Okay, and it just follows from this definition. So these are equivalent. If you, I mean, we define it like this. Another way we could have done it is to specify the probability of these singleton events. This we'll see in lecture 3. If you specify this is enough to specify the full probability measure. Because, like, I mean, um, if you have this, then for example, the probability of omega 1 and omega 2 would be the union. From the union, you can get, this is the union of these two events. And so you can get the probability of omega 1 plus the probability of omega 2. And in this case, it would be like 1 over k plus 1 over k would be 2 over k, which matches also this definition, right? So this has two elements. So you get 2 over k. So what I'm trying to say is if you specify it this way, we specify it this way, then this follows. Uh, Also, if you specify it this way, then this follows automatically via the fact that you can decompose every event uh, into the disjoint union of its singleton events, and then basically how many you have, you get that many terms here, and each one is 1 over k, so you get the cardinality of the set, which is in this case 2, divided by the total number. Okay, so these are equivalent ways of specifying it. Like basically, this is looking forward a little bit to lecture 3. This is like specifying a PMF, probability mass function. But anyways, so this is like a formal way of defining a probability model. And this is the uniform model. Okay. The book calls it naive definition. I don't like that term. There's nothing naive about it. It's just a uniform model. Any questions about this? So any finite set, you can put a probability measure on it. The simplest one is basically this one, that assigns equal probability to each event. And you can like easily see that this probably has to be this. If it's equal, because they have to sum to one, and they're k elements, so each one has to have probability 1 over k. Okay, so far so good. Questions? Okay. Um, so now I want to like uh, dig a little bit deeper into kind of because we are in the earliest stages, specifying sample spaces and such. So suppose I do another experiment. So I do two dice. So I basically toss two dice, and like I want to, for example, specify or like answer this question: is the sum being 11 like as likely as the sum being 12? This is like a historical question. So you toss two dice, and then you add them up. So for example, it could be like you get, okay, sorry, 3 and 4, then the sum would be 7. That's not the case. You get, for example, 5 and 2. Again, 7, that's not the case. Then you get like 5 and 6, for example. That will be 11. That's an outcome. Okay. So um, you get 6 and 6, that would be 12. That's this outcome. So the question is that how likely is it when I throw the two dice and then sum the two numbers? How likely is it that I get 11, and how likely is it that I get 12, and are they equally likely? What do you guys think? Any idea? No? Why not? So how do we like? Can you maybe argue Aaron? Did I pronounce it correctly? Why are they not they like? Why they're not equally likely?
I also think they're not equally likely. Probably because you can only get 12 one way and you can get 11 in two different ways.
Okay. So um, can you also write your name in the chat so that we have? So can you also pronounce your name? Maybe I can. Uh,
Yeah, sorry, I'm Jada.
Jada. Okay. Okay. Um, so okay. So the argument is that you can get 11 two ways, right? Was that the argument? And then you can only get 12 one way. Is that right?
Yeah,
Yeah. So potentially, like your argument is then that 11 is twice as likely, right? Is that
yeah, exactly.
okay? Okay. So Arun, since you can have 5 plus 6 and 6 plus 5 for 11, but only, so it's the same argument. Okay. Hayden, would it not be that for 12, both dice have to be exactly 6, but for 11, either dice can be 5 and either can be 6 um, at the same time? Y- So, Hayden, is that the similar argument that you're making or a different argument? Okay, you're essentially saying the same thing. Okay, so then, Sharanaya, like, yes, I think I agree with Leibniz. Either dice can be 6, so it's still two scenarios. So can you maybe expand on it? So you agree with Leibniz. So Leibniz said, yeah, they're equally likely because there's really one way of making 11. like 5 plus 6. And also, there's one way of doing 12, which is 6 plus 6. Uh, so, how do you agree with Leibniz? So, is it the same argument as Leibniz that you're making? Just one way of making 5 plus 11? Is that Sharanaya? Do you want to expand? Why do you think they're equal likely? Uh, can you hear me?
I don't know. I mean, I'm not sure, but if we treat like them as two different dices, like D1 and D2, then can we not say that like D1 can be 5 and D2 can be 6, and then we can like swap it to like D1 can be 6 and then D2 can be 5. And the same thing when we're making 6 plus 6, can we not say like D1 can be 6 and D2 can be 6? And then the same thing like D2 can be 6 and D1 can be 6. Like I don't know. I just thought it was like two different scenarios. I'm not sure.
Okay, good. This is exactly the thing. So let's say if you label the two dice, D1 and D2, then the two possible ways that you can get 11 are these two cases, right? Uh, and then in the same case, like, okay, if you have D1 and D2, then this could be 6 and this could be 6. And you said also this could be 6, this could be 6. I would say this is the same thing. There's no way to do, like, there's no difference in this case. So in this case, really, there's just one. If you label the dice, there's only one. Okay, and so like the whole point kind of goes back to this distinction, whether you want to make the two dice different or not. Are they different or not? Okay, so if you label them, so basically, let's say if you want to specify the sampler space in this case, if the like basically in both cases here, the sampler space would be all the like the pair like the ordered pairs, okay, ordered pairs of numbers. So if you think that the dice are different or distinguishable, then your sampler space would distinguish, for example, this and this. So, and then you'd have the cardinality of the sampler space would be 36. Okay, you have 36 choices, six for the first one, um, and um, six for the other one. Okay, and so if we do this, and then so assume we distinguish distinguish um, the two dice. They're distinct. Um, they are distinct. Then um, then we'll have like an omega which has so ordered pairs. Uh, cardinality would be 36. And if we assume that all these outcomes are equally likely, which would be like a uniform model on omega, i.e. Each pair will have probability 1 over 36. That's the uniform model that we had. Okay, so if you have 36, each one will have probably 1 over 36. If these two happen to be true, so this is now specifying a full model. Then I can answer the question. Okay, I see another question in the chat, and maybe let me read it. I think. No, because the probability P11 is 2 over 36. So two outcomes, whereas P equal 12 is 1 over is one outcome. Uh, yes, okay, so it's the same kind of argument. So if we assume that the two dice are distinct, so Alexei is like saying the same thing. So if we assume the two dice are distinct, so basically these two assumptions. And so then this the sample space will have 36 elements. And then if A2 is another assumption that if you have a uniform model, which means that all the possible pairs, like a singleton events, which are pairs of numbers, are equally likely, then I can give you an answer. Then yes. So then the probability under these two assumptions, the probability of the sum being equal 11, there are two outcomes. So it's like basically the cardinality of sum equal 11. That's that event. The cardinality of that event divided by the full, which is like 36. So you get 2 over 36. Uh, we don't have to simplify. Compared to um, the probability that the sum is equal to 12 is sum is equal to 12 divided by 36. Then in that case, just a one pair. So this would be just this event would be equivalent to just 6, 6. Okay, this event would be equivalent to 5, 6, and 6, 5. Okay, so the event that the sum is equal to 11 has two elements. This event has one element, so you get 1 over 36. So in this case, the sum being 11 is twice as likely, okay, as most of you pointed out. So now the question is that was Leibniz wrong? Okay, and like maybe most people would say, okay, yes, it was wrong, but you can see that we made a kind of a lot of assumptions to try to answer this. So if you don't make the assumptions, it's not possible to answer this one way or another. I just want to make sure that you understand the fact that probability needs kind of the model. So once you specify a model, then um, you can talk about probabilities. Before doing that, there's no way to like say whether he's okay, like is this okay or not. And I want to expand a little bit on it. So far, is this clear so far? We're gonna get to Sharanaya's like agreeing with Leibniz. I kind of like to agree with Leibniz, but I want to give you an example where maybe Leibniz was right in a sense. Okay, so this is a case. How do we know whether these assumptions are useful or valid? This is like kind of outside probability. Okay, that's the main point that I want to make. If you want to like talk about actual experiments, like you throw two dice, there's no way to, within probability, to try to validate these. So one way to do it, there are two ways. Okay, so there are actually, let me expand a little bit on this. So there are three possible models that you can think of. Like there are many more models, but one is like a reasonable model is uniform on the 36 ordered pairs. In this case, you would have the probability of like the sum being 11 is rather should write it like this. Sum being 11 is 1 over 36. Sorry, 2 over 36 versus 1 over 36 as we saw. The other one is like uniform over unordered like configurations. So if I treat, I could rather than using ordered pairs, um, which we did in the other model, I could use unordered pairs, maybe sets. We can't do sets because sets don't allow repetitions. But unordered, let me write it like this: 5, 6. This is the same thing as 6, 5. I don't distinguish between the two. Okay, so if my sample space is the sort of unordered configurations, then you can like argue for yourself that there are 21 of them. So that then if we assume that all of these unordered configurations are equally likely, then the probability that the sum is equal to 11 and the sum is equal to 12, they're equally likely. So under that model, so the sample spaces are unordered configurations, and we have a uniform model on unordered configurations, then it's going to be 1 over 21. There's a simpler model, which is like all the sums, basically, like the sample space is all the sums, and then you're uniform over all the sums. In which case, the all of them still would be like 11 and 12 will have would be equally likely, but they have a higher probability. They're only like basically how many like phase like 2 to 12 possible sums, then you'd have like 11 possible sums, and then uh, each one will have probability 1 over 11. So under these two models, Leibniz would be correct. Under this model, he wouldn't be correct. Okay. Um, Now, which one should we pick? It's like probability is silent about it. Okay. There's nothing in like a probability formalism that tells you like you should pick this one or this one or this one. But if you want to like talk about real world, let's say, and then maybe one of these models are more realistic. This is like more of a like a physical property. Like it's more of a physics kind of questions. Is this a better model for two dice, or is this a better model for two dice, or this one? Okay. Is this so far clear? I just want to make this point, get this point across. There's no way to answer this by just from a probability theory perspective. Which model? Okay. So you have to come up with the model somehow from somewhere. And most of you thought this is a more reasonable model. Um, but there's no easy way to answer it. Uh, like there's no way to answer it from probability, uh, um, from within probability theory. Does that make sense to people so far? Like it's an important point. I'm gonna continue, but yeah, okay. What would the model being uniform on 11 sums be essentially ignoring the way the sums are? Yes, I mean that's kind of ignoring that. But whether this is a useful model or not, it's not possible to. Okay, so I can try to now just try to convince you that one of these, like, you can try to say, for example, what are the consequences of these models? For example, this model implies some sort of what we'll see independence among the two dice. These two models induce some coupling. So, I mean, we need to introduce the notion of independence. But once we introduce the notion of independence, so let me try to argue a little bit in favor of one. It's not like you can pick one, but I can tell you what happens if you pick model one. If you pick model one, um, um, it is equivalent to assuming, we'll see what there's a definition of independence within the framework probability. That's one of the other, like the two other important topics. Hopefully we get to today. But from the look of it, maybe we're not going to get that far. Um, so if I assume the model A, I can show you later that this is equivalent to assuming each die is uniform on 1 over 1 to 6, and the two dice are independent. Okay, they don't influence each other. Then, as we'll see from the definition, so this is like a more primitive assumption. This might be more satisfying to assume, okay, the dice are not influencing each other. They're independent, and you might be willing to assume that. And that each one is like a fair die, or like fair dice. Sorry, fair die. And then that might be like more easily like easy to accept. So if you assume those as assumptions, then you can prove then that the probability that you get a pair, an ordered pair would be 1 over 6 times 1 over 6, which is 1 over 36. So the uniform over all ordered configurations would be equivalent to these two assumptions. So this is arguing by reducing to more primitive assumptions that might be easier to understand. And then you can, for example, argue that neither model B or C would allow this. So under model B and C, the two numbers would not be independent once we know the definition. So this is a good exercise later for B to prove that under B the dice cannot be independent in the sense that we formalize later. Okay. So with any common like law. So if they're have the same distribution, or they have the same law, they have signed the same probabilities. Let's say they're both uniform, then they can't be independent under this model B. So there's some sort of a coupling. Uh, and then that might be problematic too. You can say, okay, so there's no, let's say induce a coupling without no mechanism. So there's no way that we specify like a mechanism for this to happen. But it's like uh, still you might be okay with it. Okay. The other thing is that, okay, if it's a statement about the real world, so okay, I see another thing. So did I answer? So I think I answered Hayden's question. Would the model being uniform on 11 sums be essentially ignoring? Yeah, so that I had answered. So Atta, what is the yes? Okay, so yes is probably in response to Hayden's question. Yeah, maybe okay. I'm gonna maybe move on. So the other thing that you can do is like to do empirical work. So if you want to know actually two dice happen, like what happens to two dice, you can try to roll them many times and then see what happens. And you'd see like the sum of 11 happens twice as often. I haven't done it, but hopefully this will happen. This is like a physical experiment. And so this is a good way if you want to talk about the real world to actually do experiment. And then one of these models is consistent. If you subscribe to frequentist um, meaning of probability, then from that you can see that the model A is consistent with these probabilities. Written like the probability that would be like itself a theorem as we all discussed, but um, it's just that I mean, for it doesn't tell you anything about the physical world. So for the physical world, you do it, and then you say, okay, so we did this, and if you're frequentist, then and the model A is more consistent, like it's actually consistent with this, and model B is not consistent. So the two dice would behave like this primitive assumption that they're uniform and then they're independent. It's like a hypothesis testing problem. If you're statisticians, you have two models. You do experiment, and you'd see that okay, between these two models model A is more consistent, or actually consistent. So because like you can reject this hypothesis. This is a very simple way, like the basic like hypothesis testing problem. And so you have two models, you do experiments, and then you check the evidence. The evidence sort of matches this, or like at least this doesn't disprove this, but disproves this one. Okay, so under B, I mean, this can't happen. So there could be other models under which 11 happens twice as 12, but so far, we haven't talked about that. If you're between the A and B, then that's the case. And it also rules out C as well. Okay, so far so good. Everyone understands that kind of. So these are outside probabilities. You either reduce it to primitive assumptions that you're happy with, it's still assumptions, or you do some sort of empirical work. And then if it's about physical work, let's say, then you're essentially doing some sort of hypothesis testing. You gather evidence and then say, okay, this model is more in line. Okay, these are all outside mathematical framework probability. So far, so good. Questions? Anyone? Everyone like on the same page so far? Questions, comments? Let me pause a little bit. I think this is important. If you have questions, if it's not clear, let me know. I just want to make sure that you understand, like some of these questions that we ask, there are a lot of assumptions that you're implicitly like making. There's a reasonable assumption to make, but um, it's not at all clear. Like the introductory course, I there's usually one answer, and that means there's like one potentially reasonable like what the instructor wanted you to assume. Um, but in reality, you have to be careful that there's maybe you're making some assumptions. I mean, once you like make it formal, then you can see the assumptions, and then you can judge whether the assumptions are correct or not, or like not correct, like plausible, or like you're willing to assume. And then once you set up all that like the assumptions and the model, then the results follow. Uh, okay, so far so good. Questions? Everyone on board, maybe like show a thumbs up, thumbs up, so that I know that you guys are okay. Okay, 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 good, good. Now I want to tell you that, okay, why you should be careful is that is model B is ever like a correct model. And then people like physicists figured out much later after Leibniz that yes, in parts of physics, actually model B is what happens. So there's this aside that I'm going to quickly mention. So this is like regarding quantum mechanics or particles, like small particles, let's say. I don't know much physics, but this is a very fascinating area. So the thing that Leibniz proposed doesn't hold for dice, um, but holds for certain particles. So in fact, in quantum mechanics, you never have this situation. So the situation that we talked about is like these are called statistics. So Maxwell-Boltzmann statistics, Bose-Einstein statistics, Fermi-Dirac statistics. So the idea is that I want to distribute our particles among n states. It's like elementary particles or something like that in physics. So you have r particles and states. In this case, for example, we had two particles, and the states were uh, what are the states? Six. So this is six. You have two. Each can take six states, six like possible states, and then there are two of them. Okay. If they're distinguishable, then they can take 36. So if they're two dice kind of follow kind of the classical, the so-called Maxwell-Boltzmann um, the statistics. Okay, then the count would be n to the r. There are these many configurations. In this case, would be like 6 to the 2, which is 36. There are that many configurations. And then, so in practice, what happens in reality, this is never observed at the level of particles. This is like the classical limit, like you observe in the sorry, macro phenomena, but no elementary particle actually satisfies this. There are these two cases that are actually like happening. This is the interesting thing to make sure that you understand. If people like insisted on this, then um, uh, they would like they wouldn't be able to discover this. But people in practice, like not like I actually don't know how like the historical sequence, but certain particles behave like this, Bose-Einstein, and certain particles behave like the Fermi-Dirac. So Bose-Einstein, like the bosons, like the photon is like particles of light. They behave like this indistinguishable case. So the model B, this is model B basically. So if you have a bunch of photons, let's say two photons, they occupy like n states, their state, like the state of 5, 6, is not distinguishable from 6, 5, like physically. Um, like let's say, I guess potentially quantum mechanics predicts this, but the thing is that people like did experiments and find out that, for example, these two cases are equally likely. Like for example, that exactly like if you had bosonic dice, for example, the dice behave like bosons, you throw them and you'd observe, okay, 11 is as equally likely as 12. And so that would be consistent with this kind of model. And then there's another one which is like Fermi-Dirac, which is saying, so in this case, if you count the number of states, it would be this. I'll mention this later. So this is a combinatorial. So the number of states would be n plus r minus 1, choose r. This is a binomial coefficient. And in this case, it would be 21. And this is how photons behave. And if you have two dice that behave like photons, or like they call it bosons, I don't know much physics, but these type of particles behave like this. And then there are fermions, I guess potentially named after Fermi, I guess, now that I think of it. And then they behave differently. They can pick at most one state. So for example, in this case, 6, 6 would be ruled out. So each state would be occupied exactly once or zero. You can't have more. Okay, so this would be um, um, the behavior of fermions. This is because of this kind of Pauli exclusion principle. So these are very fascinating things that kind of, uh, uh, if you're interested, you can dig into, especially using LLMs now. So if they behave like fermions, the two dice, then the number of states would be 15, because I mean all the diagonal elements would be go on, right? So you'd have 1, 1, and so you have 6 of them, right? So these 6 wouldn't be happening. So you get 21 minus the 6, which would be 15. And if you think about it, it would be n choose r, because what we are doing is, so you have n states, and you want to pick exactly r of them and assign them to the particles. They have to be distinct. So they have to, you want to choose r distinct ones, and then the rest wouldn't be occupied. And then once you assign them, the order doesn't matter. So how many ways of choosing r uh, out of n objects with order not mattering, that's the binomial coefficient. So you get n choose r, which is like 6 choose 2, which happens to be 50. Okay, so like okay, electrons are like this, for example. If it's like correct, I double check this, but okay, so people did experiments. So they had theory. Let's say so you have a theory. If your theory looks like this, if your probabilistic theory looks like this, then it would be refuted. But if your theory sort of predicts that they're like indistinguishable, let's say if you have quantum theory that doesn't distinguish between these two states, then it matches reality, let's say. And if like in that case, in this case, it matches like it should have like also exclude potentially this Pauli exclusion is like a fundamental property like in fun like I'm assuming in quantum mechanics. So their model like has this and then they observe this in practice. So that's kind of like a perfect match between theory and practice. Okay, so you have a model of quantum mechanics that predicts that they have to behave like this way and then you count in practice and you observe these counts. So like the how often the different states happen. And based on how often they happen, you can distinguish between these models, or like you can refute this model and then say, okay, quantum mechanics is like maybe uh, matches reality better. Does that make sense to people? Okay, like there's a huge gap between Leibniz and the people that kind of observe these. Um, and it's a good rabbit hole to go down if you're interested. Okay, I'm going to stop here. Any questions? I just wanted to say that this question is not that obvious. I mean, once you write it down, there's a lot of like background assumptions that you're implicitly assuming. I just wanted to point out that this you have to be careful with. Okay. Any questions, comments? Let me ask you a question. So, have people seen this notation and choose R? How many people have seen this? Right, I don't have a poll actually. Okay. More people have seen it, or like C1, Hayden. What is n choose R? This binomial coefficient. Maybe Hayden, do you want to enlighten us? I roughly mentioned what it is, but this happens a lot in early probability because you want to count and you need to kind of distinguish between uh, how many combinations of R can you get from N? Yes, so combinations, yeah. So the right way of like in combinatories, these are called combinations. So the um, um, basically arrangements of objects with order irrelevant. Okay, so let's say 1, 2, 3. Like if you want like permutations, it would be 1, 2, 3, 1, 3, 2, 2, 1, 3. There are going to be 6 of them, right? All of them are the same, they give you the same combination. So if you want to count how many permutations of n objects are, um, actually not permutations because we want to choose r of them. So the number of choosing, let's say you have n states and the order mattered, it would be, oh, we'll see it later in the table. But this is a fundamental. Let me show you here. So if you want to count, this is just a basic combinatory. So if you have, okay, the multiplication rule I mentioned earlier. So if you have a k-stage task and there are options like n1 options in the first stage and n2 options in the second stage, irrespective of what you do in the first stage. And then and basically nj option at the state j, regardless of the earlier choices, then the total number of a's is n1 times n2 times n to the n in k. And so this leads to this n to the k if you do want to choose k objects from n objects with replacement and order matters. Okay, so the first object has n choices, and then for the second object, I also have n choices because um, it's with replacement, and then for the last one I have n choices, and these are all these things, so you get n to the k. If without replacement for the first one I get n, for the second one I get n minus 1 because I chose one of them already. And for the last one I get n minus r, so you get so n minus k plus 1. So you get this number, okay? So if the order does not matter, then if I choose without replacement and the order is irrelevant, you get this binomial coefficient, right? So you want to pick k out of n. Doesn't matter if they're ordered in a certain way, and you can't have multiple occurrences. Basically, you want to choose a set. So choose a set basically exclude the order and repetition, a set out of n objects. That's how many sets basically of size. So the number of subsets of so number of subsets of 1 to n with k elements is that much. Okay, and then you can argue this. This is like this number. Actually, I don't want to spend too much time. So you first do this, and then you divide by k factorial, because there are k factorial ways of rearranging each one. So if you have k objects, there are k factorial ways of rearranging. So you treat all of those k factorials as the same thing. So you divide by that. That's how many you get. So that's another way of writing it, is n factorial divided by k factorial n minus k factorial. So this part kind of simplifies to the numerator. And so that's kind of the formula that you usually see. But this accounts for the fact that you have k factorial permutations of k objects. Okay, that's how you get it. Hopefully people have seen this, right? Or maybe the TA also can talk about it. I'm not going to talk too much. Like this is, you can spend too much time on combinatorics, but we're going to be not talking much about probability. So this one is a little bit tricky. Have anyone seen this idea? Dividing by the number. Hoping that you've seen this. If not, I mean, come ask me, or we can like work it out with ChatGPT or so this one is more tricky. I'm gonna let you read this. So this is kind of the stars and bars approach. So basically you reduce the problem to counting a different like set of things. Basically, you have a set of bars and the stars, and then they kind of these divide basically the stars into the different bins. And so this, for example, configuration gives you 2, 0 because there's nothing in the middle bar. And then 3 because of this, and then 2. And the way to, I mean, every one of these stars and bars strings would give you like a valid configuration where you order is irrelevant, but you can have replacement. So these are like basically telling you that so let's say if you have 4 objects here, yeah, you want to have 4 objects. 2 of them are of the same type, 3 of the other type, 2 of this type. So if you have like, maybe in this case would be like, you have, what are we doing here? You have k objects from n types. So types here would be, how many objects are we? So k is the number of stars. So here would be like 1, 2, 3, 4, 5, 6, 7. So k would be 7. And then we have n minus 1. So you have four objects. Sorry, 4 types. 7 objects, 4 types. And And then you can count um, these by um, basically you get n minus 1 plus k factorial ways of rearranging, but then the stars within can be rearranged and then the bars can be rearranged. So you get n minus 1 factorial and then k factorial, which gives you n minus 1 plus k, choose k. So I'm not going to spend too much time on it. I mean, you have to think a little bit about it. It's a little bit tricky, but that's how you get it. And you can like, translate it into the string of stars and bars and then count these configurations. And you can see, for example, if I switch these, it doesn't change the configuration. That's what it's trying to, like if I switch the bars within themselves. So if I move this to this part position and this one to this position, doesn't give me the same configuration. That's like the correction that you do. Okay, so this table is like the basic idea, and you can see that these numbers are kind of appearing um, in this table. Any questions so far? This was a little bit fast, but I just wanted to not spend too much time on combinatorics, hopefully. You're gonna practice a lot of this, maybe in the homework problems. Questions? Comments? Okay, and then also the book has something about like they call it story proof or proof. Yeah, story proof, something like that. But basically combinatorial proofs, you can like um, play with these um, like combinatorial identities or like try to prove them by counting the same thing in two ways. So if you have, for example, want to pick a k-person committee with a designated chair, there are two ways of doing it. I'll let you read it. And then depending on how you choose, um, uh, like for example, if you choose the committee first and then the chair versus you choose the chair first and then the committee members next, you get seemingly two different answers, but they have to be equal because basically they're counting the same thing. So you get these identities. That's an example. So the combinatorics, I would say you should practice on your own and then maybe come to office hours or talk to the TA about it if you have problems. Okay. So far, so good. Okay, you still haven't finished the material from lecture one. So I'm gonna rather do these two other examples quickly. The other example that we can do here is to give you kind of it's not, I would say it's not as deep as this question of two dice, but it's also a question that is very famous. So how many people have seen this birthday problem? If you have a room like full of K people, and you want to ask how large should K be for at least two people to have the same birthday, uh, or rather, the probability that at least two people have the same birthday is at least one half, right? Have you seen this problem? It's called the birthday problem. So, for example, we have 13 people here. Is this enough for us to have the probability that two of us have the same birthday is at least one half or bigger than one half? Do you think there are enough people now or not enough? How many people do we need? Have you seen this problem before or not? Do you have a guess? If you haven't looked at the slides, do you have a guess of how many people? Is it a big number? Is it a small number? Again, like the underlying assumption, like first you have to have a guess maybe. Maybe let me see if you guys have a guess. Any guess? 8. Okay. So you're too optimistic. Eight. Anyone else? Usually people guess a much larger number. 8 wouldn't be enough. You need more. Anyone else? Aidan said 8. Anyone? Any other? Oh, 365. I like that. Okay, so we want big numbers. Yeah, that's kind of 500. Good. Okay. Now you're talking. It's like if it was an auction, we could give it to the person who proposes the largest. Medium amount of people like 20, 35. Okay. It turns out that Aaron is actually right. I don't know how your intuition. Have you seen this problem before or not, Aaron? 536, like 365 is larger than what we need. 8 is smaller, but 20 to 35 is right. Have you seen this problem before, or you just made a guess? Very close saying it a lot. Okay, okay. So you have seen it. So usually people don't have a good intuition about this problem, but that's kind of the right guess. So the answer turns out to be like 23. But what I want to say is you still need, if you want to answer this, the key point I want to make is that you still need a model. Okay, you need to be willing to assume something to be able to answer this. There's no like unique answer unless you make some assumptions. This statement is not, it's not possible to answer this within like the framework probability unless you specify a model that allows you to specify probabilities, basically. You have to sort of implicitly do this. So one way to do it is say, okay, let's say ignore the issues with the February being 29. There's like seasonal effects, like maybe uh, some years are longer, some years are shorter. Um, let's say we have 365 years in each, sorry, days in each year. And if you assume that uh, all the possible ways that the people, um, all the configurations basically, so everyone has this many choices for their birthday. And so you get, if you have k people, you have this many configurations, okay, k times. So you get 365 to the k possible configurations. If you assume that all of these are equally likely, basically you have a uniform model on this huge space of configurations, then, for example, we can answer this problem because this would specify all possible events that we want to talk about. So this will give me a sequence of dates of length k. And you can see it's like a huge number because it's like this to the power k. So if you have 20, this would be very large. Then we can answer this question. So basically, we're treating it as ordered, like uniform unordered sequences. Okay, because like I'm different than you, let's say, and so we're in that kind of the Maxwell-Boltzmann kind of setting, if you want. This you can also reduce to the primitive idea that, okay, people's birthdays are independent. We can like later show, or we can argue that this model is equivalent to assuming that the birthday for each person is independent of everyone else, and each one is uniformly distributed on 1 to 365, similar to the dice case. Okay, so this might be easier to swallow than just saying it's uniform over this huge space. But that's equivalent. Okay, so if you're willing to assume that basically what day I was born does not influence anyone else's, let's say, they're kind of completely independent of each other, which is a reasonable assumption, then we can make a lot of calculations. So the answer would be 23. So the way to do it, how do you do it? Let's say if you have the model, how can we write it down? Anyone? Um, Just see if you can. It's like a tricky problem. So once I specify the model, I can do it. One way is to try to count, like, right? So the model would be just that uniform model. I have to count how many choices there are. So there, like, we know that the full space has this many. Then I have to compute all the possible um, sequences of birthdays in which two persons have the same birthday. Okay. If we encode the days 1 to 365, so for example, it could be like the first person is 300, the second person is 21, and then you go and then there's another one, it's 21. Okay, so this satisfies the criteria versus another one in which um, all of them are different wouldn't satisfy. So you have to kind of somehow count. Um, but the idea is like there's one like easy way, like one event is easier than the other. Sometimes you can translate this event to another event that you can count better. Anyone wants to pitch in, like how to compute this probability? Okay, in the interest of time, I'm going to do it myself. So what happens is that the complement of this is easier to compute. So if this event is A, okay, you compute, this is a trick you often do probably. You compute the probability of the complement, uh, which is going to be by the properties of the probability would be 1 minus the probability of A, okay? So if I manage to compute this, then another way of doing it is like P of A is like 1 minus the probability of A complement. Okay, so I can compute this and then I can easily do it. So complement would be, what is the complement of this event? This is a logical kind of construction. So this is saying at least two people share a birthday. Logically, what it means to complement this, basically negate this statement. Anyone? No two-person I should answer myself, should have the same birthday. So at least two, the negate would be like no one, no pair. Okay. So basically all people have distinct birthdays. So the number of those, so the count of that event, so this would be like, let's say this would be a complement. Um, the count would be, I can assign the first person its birthday. I have 365 ways of doing it, but for the second person, I have, sorry, one less choice and so on until I get 365 minus k plus 1. I have this many ways of assigning uh, uh, the birthdays without replacement, basically. Okay, and so if this is going to be the cardinality of a complement, and this is the cardinality of omega, so you get this number. And so this is the probability of no match, and so you can write it in this fashion. Okay, so if you divide basically um, what we are doing is that you're expanding this, right? So this is really 365, 365, 365, and you basically match each one of them, and then you form a fraction. So you get the first one would be 1, the other one would be 1, like our 365 minus 1 divided by 365, so you get 1 minus 1, 365, and then in general you get 1 minus j divided by 365. So that's the probability, okay? And so the probability of match would be 1 minus this. Okay, so 1 minus the probability of no match. And you can form a table, and then you can see like at 10, it would be like 0.1. So at 8, for example, it's like less than 10%, or like maybe 10%. I don't know. At 23, it would be like above 0.5. And it quickly saturates. Like if you have 70 people, it's like 99.9% chance that two of them have the same birthday, which is maybe counterintuitive. Okay, does that make sense to people? So you specify a model. Once you specify a model, you can kind of, because we're in the uniform model, you just count the arrangements. And sometimes it's easier to count the complement event, the arrangements in the complement event. Sounds good? Questions? So questions? So this may be like some people might have like a different intuition. I mean, if you, for example, ask, I fix myself, or like you fix yourself and ask, what is the probability that someone has the same birthday as me? The answer in this case would be, like you can easily argue, this case would be like this, because um, you fix your own birthday, and then the there are this many possible choices for, or rather, this many ways that someone else can have. Uh, sorry, this many ways that no one else has the same birthday as you. And so this is the probability that no one has the same birthday as you. So this is going to be that probability. And this is much larger. So for this probability to be passing one half, k has to be much larger. The thing is that in this birthday problem, there are k choose 2 pairs actually. And this kind of is why this number is much lower. So there roughly this is like k times k minus 1 over 2. There are more possibilities of collision basically in a way. If you want to write it down, an easy way of doing this is to, and you'll see this later in the computation of the what's called expectation, but an easy way to see this k choose 2 happening or coming up is if you have, let's say, 1 minus x and x is small, okay, then a good approximation would be e to the x, or minus x, sorry. If you do the Taylor expansion of e to the minus x, will be 1 minus x plus x squared, I believe, over 2, and so on. So if you ignore the higher order terms, it's approximately 1 minus x. So in probability, sometimes, I mean, in these calculations, we do approximation the opposite way. So I can approximate this by, let's do this. Approximate with, this is like x, okay? And if, let's say, k is small relative to 365, this is approximately what it would be. It would be e to the negative j 365, okay? And then when I do the product, you sum. The product turns into a sum if you do the exponential. So you get sum j divided by 365. So that thing is easier to compute. And then you'd get, so the sum j from 1 to k is, anyone knows what the sum is? One of the questions that Gauss kind of did. So if you do, so basically we get something like this. So you'd get e to the negative 1 plus 2 up to k divided by 365. And then you have to calculate the sum. The sum would be k choose 2. Sorry, the sum would be up to k minus 1 actually. Let's see. Yeah, so the sum has to be going 1 up to k minus 1 because there's a, so you can see like there's a, this goes from 0 to k minus 1. And so you get, actually I'm a little bit, let's see. To worry a little bit about the 0 case here. You may have to go from 0 to, this might have to be 0. We'll check. But okay, I also have to check this. But roughly this would be of the order of k choose 2, which is like k times k minus 1 over 2. Okay, so what you get is quadratic. Basically, they're of the order of k squared. So this would be like e to the negative um, k times k minus 1 times 730. Okay, so this is an approximation to the probability of no match. And so you can see because this is quadratic, it like this exponential drops much faster. Than, for example, this case, this you can approximate 1 minus 365 to the k. This is approximately e to the negative k divided by 365. Okay, this is linear in k. Um, uh, uh, 1 minus 1, 365 to the k. This is approximately using the same approximation would be e to the negative k divided by 365. So k divided by 365 versus like roughly k squared divided by, and there's a 2 as well, but that's fine. So this is like basically e to the negative ck grows much slower than e to the negative ck squared, or even like if you do half here. Okay, this is like the power of the exponential ones. This is how, like, for example, the tails of a Gaussian, we'll see. This is how they drop. And so this is much faster. And so the probability of no match quickly goes down much quicker than this probability that someone else doesn't match you. So this is the reason why this number is so small. And then you can, for example, using this approximation, you can set it equal to 1/2. If you take the log, you get log 1/2 is equal to negative k minus 1 divided by 3, like 730. And so you put the negative sign on the other side, you get log 2 k minus 1, and then multiply on the other side, 730. And then 730 is really, it's like 2n. Okay, n here would be the number of states or basically days. Okay, so that k has to be roughly of this order. If you imagine this is approximately k squared, so k has to be of the order of root 2n log 2. Okay, would be a square root of n, or like 2n. That's why it makes it smaller. And the same kind of idea is for example, this is you can call it the collision. If you imagine this is like um, in computer science and matters because you could have a similar problem happen. So you have like you assign the hash, which is a 60, let's say 64-bit, let's say any number of bits. So you create a 64-bit um, string at random and assigns to objects. So you want different objects to have different hash values. And if you assume that they're independently assigned and you have this procedure for uniformly assigning like a 64-bit hash value, then you want to know how often could it be that there's a collision, like two objects have the same hash value. That's kind of the opposite of what you want a hash function to do. You want it to basically distinguish uniquely different objects. And so then you can compute, for example. So this would be like 2 to the 64. And then like k would be like that n would be 2 to the 64 because that's how many possible hash functions you have. Then like k would be of the order of basically um, root n, which would be like 2 to the 32, which is you need that many items, like 4 billion, I guess. Um, and not this many. Okay, so it's like much smaller number for a collision. Okay. And that's reason this is, for example, you need maybe a bigger, uh, like a larger uh, hash string if you have more than like 4 billion items. So the same kind of situation happens. This is answering like a uh, interesting problem in computer science, like the probability of a hash collision if you do it at random. Sounds good? Any questions? Uh, Comments? I'm gonna maybe skip the next. There's another like example here because we're out of time. Not out of time, but this is another problem of classical. So suppose you have like a secretary which is completely absent-minded and they have to put like n letters into n envelopes. Um, and they like kind of completely at random put them completely at random. And then the question is that you want to like ask what is the probability at least one letter is placed in the correct envelope? Um, Again, you can start from some sort of a uniform model. In this case, it would be uniform over all possible arrangements. So you have these envelopes, for example, as positions. So you specify like envelope 1 up to n, and then the assignments of letters to envelopes would be a permutation, basically. Like you'd have n factorial, basically, permutations or arrangements. And we're going to assume, for example, that all of them are equally likely. So you're a uniform model on this arrangement space. And then this problem, um, you have to, again, do accounting. And this is where this idea of kind of a, um, uh, I mean, this is a little bit harder than the birthday problem. It's a union of events. So for example, if you have the event that AI is, the event AI that the letter I is placed correctly. The ith letter is placed in the um, correct envelope, then the event that we want, you can write it as the union. Okay, so this is saying at least one AI happens. Okay, which is saying at least one AI, one letter is placed correctly. So these events, you can think of them as the basic events, and then the event that we want is really a union. And sometimes you can try to flip it. For example, I could try to say, okay, this is 1 minus the probability of um, um, the intersection of the complements, but that's not easy as well. In this case, this is an example where you can actually use the full. So we saw, for example, the probability that A1 union A2 is the probability of A1 plus probability of A2 minus the probability of A intersect A2. So this, if you generalize, there is a so-called to n events, there is a general formula uh, which is um, which is called inclusion exclusion. So it's in the notes, and basically you have to compute the probability of all possible intersections of these events, and then in this case, in this problem, it's easy because all these possible like the probability depends on not the particular events, but how many of them are they. So if you, for example, imagine this event, this is saying letter I1, letter I2, letter I2, up to letter IK have been placed correctly. It doesn't matter which I1, I2, IK. Then you can argue that, okay, so if I place K of them correctly already, um, um, then I have N minus K remaining positions. Uh, and all of them are going to be still equally likely. This is easy to kind of argue, or at least you don't have to argue it like that. So there are this many positions, and basically these many ways of assigning n minus k remaining um, letters into these positions. There's n minus k factorial. So that's kind of the numerator, and the denominator still is like n factorial. So that these probabilities are easy to do by counting. And then uh, how many of these events are there? There are these many, and then you like combine them into that exclusion inclusion formula. I'm not going to go into the details, but this is something that um, you could look into the notes, and if you have questions, uh, you can come to office hours or maybe bring it up in the discussion and can be answered. Okay. Okay, so far so good. I think that finishes what we wanted to do in lecture one, actually. So now almost lecture two as well. So any questions? the basic kind of idea of probability and basically the uniform model and a lot of discussion about like the assumptions underlying these kind of in these type of questions, you're making some assumptions here in the birthday problem and in the two dice example. Okay. So that took us a while to kind of get through, but I think it's important. Any questions? I'm gonna pause maybe like a little bit, a few seconds. So far, so good. Okay, one time's up, thumbs up. Anyone else has a like a comment, question on board? Let's see. Okay, so let's start something fairly interesting, which I doubt we can get all the way through, but that's basically the second most like important idea. So they're like basically, okay, quick question. Uh, are we only going to be testing on material that's on the slides and lectures, or will there be things? So mostly, yes, yes. What I talk about in the slides and also in the notes, mostly that I post. Um, and potentially, you can. I mean, I'll try to, yeah, to restrict to these. But you're welcome to read the book as well. So the chapters that I assign, if there's anything there. Yeah, but my focus will be on the things that I talk about. And it's hard to pin it down because you can ask a lot of different questions. You come and reading the chapter before or after. It's up to you. It's up to you. And I'm not sure if I posted the notes already, but if I haven't, I try to post lecture notes as well, which are like more expanded version of these slides. I think I have potentially. Uh, oh, I haven't posted the lecture notes. Okay, I'm gonna post the lecture notes. I think I have a set of lecture notes that maybe the first three chapters I'm gonna post. You're welcome to read in any order you want. Yeah. Any other questions? Okay. Um, so let's talk about the most the second most important idea, and that idea is like the conditioning idea. Um, so the idea is like you have a let's say like a probability model. So we have a good foundation now, so we know what the probability measure is, and we have one example, let's say uniform, which is often good absent any external assumption, or in cases where you have symmetry. But suppose I have a probability model and then I observe some data, and then somehow I have new information now. Um, for example, I like throw the dice and someone tells me I don't see the outcome, but they tell me that the sum is equal to 7, for example. Okay, so this is new information now. And in the light of this new information, we want to revise our probability statements. Okay. And this is again like a definition, but it kind of intuitively matches our ideas of how a revision should be. Again, this is a lot of the statistics is about this idea. So we're going to spend some time on this. So you have a model, sometimes called the prior model of the word, and then um, actually you can have multiple models, and then you observe data and you want to like adjust your model. Okay, and this leads to the idea of first, conditioning is what allows you to do this. So we have to define conditional probability, and then there's some results related to this, which is like the chain rule or the law of total probability. And then I have like a specific way I want to like basically connect it to statistics, which is sometimes you be able to partition um, the set of all possible outcomes into disjoint sets. And these are possible states of the world. And then we can try to query like which possible state we are in. And then this leads to the idea of likelihood and the Bayes rule and and we'll see this famous example. There's another famous example like the birthday problem, Monty Hall problem, which is like very counterintuitive. And then also talk about independence. Okay. Um, okay, let's get into it. Uh, so this is the question. So we have a probability space, omega. I usually write it as I omitted this because we don't specify this as often, but in formal probability, you have to also specify the set of all events. So we have a probability space for the experiment, and then an event occurs, an event B occurs, and we don't know anything else. So the question is that how should we update? Um, so the idea is that we're going to have an updated probability measure. So you're going to turn this into potentially, which I should write it like this, a Q, which is a new probability measure. And this is the idea of conditioning. You revise your entire probability model. So there's a definition, but before giving you the definition, I want to like basically convince you that there are these two properties that we want, and these would kind of basically uniquely specify the formula. So the first one is that because I know the outcomes outside B are not and they did not occur, I want to assign zero probabilities to them. Okay, so I know B has occurred, so whatever new probability model we have should assign zero probability. Okay, so this is going to be our new probability measure. We'll assign zero probability, sorry, probability one to B actually, zero probability to anything outside. So if uh, A does not intersect B, so sorry, intersect B is empty, then the probability of A, no, not the probability, this is the new probability. The probability of the new event would be zero. Okay, so anything that does not intersect. So we know that B has occurred, let's say A is here. So none of these have occurred, so we have to assign zero probability to that. Okay, this is very reasonable, I would say. But now this also tells me for a general A, now if I have a general A, imagine the A is like this. I know that this part didn't happen, so we are assigning zero probability to that. So I would see that whatever new probability we assign to this, so if you like a, let's like for a general A, I can write A as uh, uh, basically whatever is not in B, that's the set difference, union intersection of A and B. Okay, so this is the intersection. This is the intersection, right? And this part is uh, that part. So uh, we are assigning probability measure. So this Q of A has to be additive. So it has to factor like this plus that, right? And this part, by our requirement, this is going to have to be zero. Okay, so we see that the Q of any event would be the same as the Q of the intersection. Okay, so we get this property out of this requirement that whatever new measure that we want to have, the probability assigned to events A would be the same as the probability assigned to the intersection of that event with B. This holds for all A. Okay, so this follows from this requirement. The other natural requirement is I want to keep the relative probabilities within B the same. So what do I mean? It means that if I have two events that are inside B, so I have B, and I have A here, and I have another A prime, for example, it could have intersection with this. Okay, so but they're both inside B. What I want is that the relative probability of these two shouldn't change. This is also reasonable. So the probability that this occurs, let's say this is new QA, and then the probability that this occurs is the new QA prime. The ratio I want to have the same, be the same as the previous ratio. Okay, relatively how, like let's say we had like for example, like an example of this. So um, the probability that the sum is 11 in the two dice experiment is twice um, as likely as 12. And let's say if the conditioning event, whatever event occurred, includes both of these events, then we want to say that okay, still the ratio should be the same because there's nothing the new information doesn't tell you anything about the relative behavior of these events. So this is very natural, I would say. Okay, so if you accept this, this is not a not a requirement necessarily, but it's like a natural thing. If you accept these two, then we can drive what um, the formula for Q actually has to be. Okay, is this your second requirement kind of clear? We want the relative probabilities to remain the same if they're both inside B, because we don't have any more information about the information is just saying that nothing outside happened. It doesn't tell me what happened inside B. Okay. So whatever situation, relative situation should kind of remain the same. That's kind of the reasoning. Okay. So if you agree with this, then for example, from this, I get Q of A is equal to Q of A intersect B. And then from this, I can say, okay, Q of A intersect B divided by Q of um, an event which is inside. So this is inside. So this is inside B. Uh, and another event that's inside B is B itself. So this has to be the same as PA intersect B divided by PB. Okay, because both of these events are inside B. And now if I combine the two, you can see that Q of A is, so okay, so this one is also, by definition, is going to be 1, because you're assuming that uh, Q of B complement from this is 0 from R1. Okay, anything outside B is 0, so Q of B is actually 1. So this would be 1. And now you can see that this is equal to this, which is also equal to Q of A. So Q of A has to be equal to this guy. Okay, so these two requirements give me this formula for conditional probability. Okay, so once the dust settles, you get this formula. This is the Q of A that we had. It's a new probability. We'll see, or actually you can prove that this is actually a probability measure. But the notation we write for it is PA given B. Okay, this is called given. So this is the notation. This is really definition. Um, but if you assume that these two requirements have to hold, then you can say this is the only measure. This is the only probability measure that satisfies these two. Okay, so this is the definition of conditional probability. We say that if let's say probability of B was positive, uh, uh, then the conditional probability of A given B is this quantity, P of A intersect B divided by P of B. Is this kind of reasoning clear? Questions about this? Are we going to be tested on proofs? I wouldn't say this is a proof, actually. It's going to be multiple choice, so as much as you can test. But this is really not proof. It's just a bunch of probability. Like for example, you should know this, right? The fact that QA is QA, like this is from additivity of probability. If I add, okay, we could do it with P. But if I ask if the statement is true for a probability measure, then you should say yes, it is true, or something like that. Any other questions? I mean, the argument you don't actually meet, so you can accept this as the definition of probability, the conditional probability. That's how it's often presented. I just wanted to give you some justification where this comes from. Like, again, this is like more primitive. It's still like I'm not proving anything. It's just saying that if you agree with these, then conditional probability should look like that. Okay, it's worth going through this little argument that I did. I mean, first time you see, if you haven't seen this, it may seem mysterious why we wanted to do this, but it's really natural if you agree with those two requirements. It's like basically, again, the principle of reducing it to something which is easier to swallow. But you can forget that it's just a definition, okay? You write probability of A given B. This is saying B has occurred. Now, what is the probability of A? And this is the definition. You do the probability intersection. We have this. Divide the probability of B. And you can easily verify that this is really, let's ignore the, um, this is really a probability measure. So what happens is, okay, this settles. I'm going to go back. I'm going to skip the example. This example, you can read about it. It's just not that important. I don't know why it scrolls slowly. So what you can show is that this map that maps A to this P of A. Are you seeing? I don't know why it's so slow now. Uh, are you seeing what I'm writing here? Okay, you see probably. Yeah, it's like there's a lag. So the map that maps A to PA given B is satisfies all those three axioms. So it's really a probability measure. So for example, P of um, I can say P of omega given B is actually 1. Um, in fact, P of B given, and then P of A given B is non-negative, and also the additivity, like probability of A union A2 given B factorizes probability of AI given B if uh, basically if these are disjoint. Okay, so what it's saying is that so all the because it's a probability measure, all the properties we discussed in chapter 1 about a probability measure hold. So the complement rule, inclusion, exclusion, which will be in the notes, union bound. For example, the probability that A union B, sorry, union A1 given B would be less than or equal to probability of A, sorry, A2. A1 given B plus probability of A2 given B. Okay, mentally you can basically disregard this, and you can say it's just saying probability of A union A2, A1 union A2 is probability of A1 plus probability A2. And this is valid because this is still a probability measure. It's just a revised probability measure, but it's still a probability measure. It satisfies those three axioms. Everything that the probability measure satisfies, this will satisfy. The complement rule would be like probability of A complement given B would be the probability like 1 minus probability of A given B. So we don't need to verify all these properties again. Uh, it just it's enough to verify these three, and you can verify like these two are very easy to verify, and this one also follows. This follows from the fact that, for example, if you do A1 union B, sorry, union A2 intersect B, it would be A1 intersect B, union A2 intersect B, and these two pieces would be independent, basically. Sorry, uh, if these are disjoint, then these would be disjoint. So this one, the additivity requires a little bit of work. But once you verify, and this is a proposition that they really it really satisfies, then all the properties that we had automatically follows. You don't need to prove them. Okay. So that's the first property of conditioning. The other idea is like kind of basically it's a way of renormalizing. Basically, we normalize so that you can see that if you look at the definition, okay, so this notation also means the dot, it just specify. This is saying we look at this as a function of its first argument. It's exactly this thing. So it's saying that this thing as I vary the first argument. Another way of saying it is like this mathematically. So this is the same notation. When I say something like dot here, it means this is a whole function. It takes uh, an argument here, and we're viewing it as a function of that argument, which would be a set. So this is a measure. And the idea is that, um, for example, if you look at the B given B, the probability of B given B would be probability of B intersect B divided by probability of B is just going to be 1. Okay, so this assigns mass 1, like the total probability mass to B. Um, and so basically, effectively renormalizing everything to B. It's as if we know that everything in B happened with probability 1. Originally, under original model, the probability of this B could be less than 1. But the conditioning, once we do the conditioning, by definition, the probability of the entire set B is 1. Now it's as if I restricted my sample space to this. Okay. Um, uh, like okay, in a Bayesian reading, you can think of the P as your prior belief about events, and these are like your posterior beliefs, beliefs after, beliefs before they're called prior, beliefs after they're going to be called posterior. So it's like conditioning is a way to change your measure, probability measure, from one, which is the prior measure, to another one, which is the posterior measure. It's not like an ad hoc patching. It's just basically a renormalized to a new measure. Um, okay, just one more slide and then I'll stop. The important thing is that these two are not the same. The probability of A given B is very different from probability of B given A. Okay, so this is saying A has occurred. Now, what is the chance? What is the probability of B? This is saying B has occurred. Now, what is the probability of A? And this is highly non-symmetric. Uh, and the way to translate back and forth is via this Bayes rule. Um, and this is the source of a lot of fallacies, like or counterintuitive like ideas, like in medical testing. In medical testing, kind of the difference between these two would lead to some incorrect conclusions, and also in courtrooms, like this is called prosecutors' fallacy. Like they did a DNA test, and it's very unlikely that it's a match, then therefore this guy is guilty. That's kind of the interesting fallacy uh, that it's very similar. Uh, yeah, okay. So I'm going to stop here. The office hours I mentioned, I think early in the early. So this week is going to be on Friday, and I'm going to post the time, most likely at 3 to 4. But in general, it's going to be on Wednesdays after the discussion, which is going to be 5 to 6, I believe. And the Zoom link, let me try to maybe I'll create a different Zoom session for it, and I post the link. Okay. Any other questions? Questions, comments, me? Stop the recording.